What if software could govern itself? Imagine a system where AI agents don't just generate code. They execute inside a governed runtime, where every action is visible, every state change is traceable, and intelligent decisions coexist with deterministic logic in a single, auditable structure. That system exists. It's called Agentic-Nets OS. 10 services, over 182,000 lines of code, 7 transition types spanning deterministic routing, data transformation, API calls, AI inference, autonomous agents, remote command execution, and knowledge graph navigation. A visual editor where you drag and drop workflows. A query language for filtering data. A CLI that talks to 5 different AI providers. A Telegram bot. Full monitoring with Prometheus, Grafana, and distributed tracing. A Jenkins pipeline that deploys autonomously to a staging server. One developer built all of it in 9 months, with coding agents as the only collaborators. This is the story of how that happened, and why it took 20 years to begin. An idea that waited. This story really starts in a university lecture hall over 2 decades ago. I was working on my diploma thesis in computer science. The subject, Petri nets, mathematical models for concurrent, stateful systems invented by Carl Adam Petri in the 1960s to describe chemical processes. But the formalism turned out to be universal. Anywhere you have state, concurrency, and synchronization, Petri nets describe it naturally. For my thesis, I built a Petri net simulation engine. XML for the token definitions. A graphical editor where you could draw places and transitions, connect them with arcs, and watch tokens flow through the system in real time. It wasn't production software. It was academic work. But something fundamental clicked. Here's what makes Petri net special. A net has places, containers that hold tokens, which carry data. It has transitions, operations that consume tokens from input places and produce tokens in output places. And it has arcs, connections that wire places to transitions and back. A transition can only fire when all its input places have tokens available. When it fires, it consumes input tokens and produces output tokens. From those simple rules, you get concurrency for free, synchronization for free, explicit visible state, deadlock detection, a mathematical formalism studied for 60 years. After graduation, I moved into professional software development, enterprise systems, integration platforms. I became a software architect, event sourcing, CQRS, distributed state, fault tolerance. The kind of architecture where getting the fundamentals wrong costs months of rework. But the Petri net idea kept coming back. I'd look at a fragile chain of API calls and think, this should be a net. I'd watch a workflow engine struggle with concurrent branches and think, Petri nets handle this naturally. I'd see teams debugging in visible state and think, in a net, that state would be visible. Over the years, I built several versions. Different languages, different frameworks. Each one taught me something. None became a product. The gap between the idea and a complete implementation was always too large for one person alongside a full-time job. The idea waited. For over a decade, it waited. The moment everything changed, in late 2024, AI coding agents arrived, not as novelties, but as genuinely capable development partners. Claude, Codex, Gemini evolved from clever autocomplete into tools that could understand context, write substantial code, and reason about architecture. And I had a thought that hit me with the force of something I've been waiting to think for 20 years. Now is the time. Not just to rebuild the Petri net engine, to reimagine it entirely. What if some transitions were intelligent, powered by large language models? What if you could embed an AI agent inside a transition, giving it access to the net's state, the ability to call tools, and even the power to create new structure? What if transitions could define semantic relationships between places, turning the net into a navigable knowledge graph? What if each net was, in effect, an agent? That was the idea that launched Agentic-Nets OS. And I would build it with coding agents. One developer, no team, just me and the AI, learning to build together. I started the way most people start, badly, throwing prompts at the model and hoping for good output. It felt productive. It wasn't. The output was inconsistent. The patterns drifted. The turning point came when I stopped treating the AI as a search engine that writes code and started treating it as a development partner that needs clear specifications. Instead of write me a persistence layer, I would describe the event model in detail. What events exist, what they carry, how they relate, what the read model should look like. Then the AI would generate coherent, architecture-aware code that fit into my existing patterns. I developed a working method. First, I decide what needs to exist, how it connects, what the contracts are. Then I write a mini spec, what changes, what edges it touches, what tests should verify. Then I hand it to the coding agent. The agent implements. I review. We iterate. Small slices, tight feedback, tiny diffs. When the cost of trying an approach drops to near zero, you stop agonizing over choices. You try 3 persistence models in a week. Generate both approaches in parallel. Test both. Keep the better one. You optimize for learning speed instead of upfront correctness. 7 transition types. The heart of Agentic-Nets OS. The core innovation is the transition taxonomy. 7 types across 4 lanes. This is what makes the system fundamentally different from every workflow engine and agent framework I've encountered. The first lane is deterministic. These transitions cost nothing beyond compute. No AI involved. Fast and predictable. Past transitions handle routing. A token comes in, conditions are evaluated, the token goes to the right place. Like a railroad switch. Emit rules route tokens to different output places based on their data. If the status is success, send it left. If error, send it right. Zero cost, infinitely reliable. Map transitions handle data transformation. They reshape tokens using a template engine, variable substitution, structural mapping, data extraction. The input token has one shape, the output token has another. No intelligence required, just mechanical transformation. HTTP transitions make external API calls with enterprise-grade reliability. Retry with exponential backoff and deterministic jitter capped at 250 milliseconds to prevent thundering herd problems. Multiple authentication methods. Basic, bearer, API key, OAuth 2 client credentials with automatic token caching. Idempotency via TTL-based request deduplication. Configurable success codes. Error routing via emit rules. The second lane is intelligence. This is where AI lives. LLM transitions make single inference calls. One question, one answer. Classification, summarization, code synthesis. The transition fires, the model responds, the response becomes a token. Agent transitions are the most powerful construct in the system. Autonomous multi-step executors with access to 39 tools organized across 4 permission tiers modeled after Unix file permissions. Read, write, execute. HTTP. A read-only agent can query tokens, list places, inspect net structure, export topology, but can't change anything. A read-write agent adds the ability to create tokens, build new places and transitions, set inscriptions, heal broken configurations with a net_doctor tool. A read-write-execute agent can deploy transitions, start and stop them, fire them, run Docker containers. And a full access agent gets everything including external HTTP calls. The third lane is execution. Command transitions run shell commands via remote executors. The executors poll the master for work. They reach out, not the other way around. This egress-only pattern means executors work behind firewalls without requiring inbound connections. And the fourth lane is structural. Linked transitions define semantic relationships between places. They never fire at runtime. They never consume tokens. They have no action block. Their purpose is purely structural. They build a navigable knowledge graph inside the net. An agent investigating an incident can call GTLINKPLACES and discover that the runbook's place is connected to the past incident's place, which connects to the lessons learned place. The agent follows these connections to gather context, building understanding through the net's own topology. Link transitions turn a workflow into a knowledge structure. 7 types. For lanes: pass, map, HTTP, LLM, agent, command, and link. The deterministic ones cost nothing. The structural ones define relationships without execution, and together they can express any workflow I've ever encountered in enterprise software. ArcQL, a query language born in an afternoon. Every transition needs to know which tokens to consume. In Agentic-Nets OS, tokens carry rich JSON data. You need to filter. I designed a grammar on a whiteboard. From $, where $.status equals active, order by $.timestamp, descending limit 5. Then I gave the specification to the AI. What came back was a hand-rolled recursive descent parser. No generative frameworks, just clean Java code walking through characters one at a time. Context-aware tokenization handles UUID segments in paths. Proper string escaping. Number detection. Boolean and null support. And or operators with correct precedence. Working query language in an afternoon. From grammar design to tested parser to integrated evaluation. The mechanical translation from grammar rules to parser code is exactly the kind of work where AI delivers extraordinary speed. The backend, event sourcing at scale. Java 21 on Spring Boot with reactive web flux. I know the ecosystem deeply, and reactive programming maps naturally to concurrent transition firing. The data engine is a metafile system built on event sourcing. Every mutation is an event. The complete history is replayable. CQRS read projections provide fast queries without sacrificing the audit trail. Token reservation uses atomic compare and swap for exactly one's consumption. Coding agents shined here. The mechanical work, event handlers, projection builders, repository interfaces, API endpoints, all generated by the AI. I designed the architecture. I defined the contracts. The AI implemented them. 42 API endpoints generated from an open API specification in a single afternoon. The node service runs to 34,000 lines. The master to 96,000. Together with the front end, the system exceeds 182,000 lines across hundreds of files. One developer, 9 months. But the real story is in what that code does. The front end, Angular taken to another level. I'm comfortable with Angular. I've built production front ends before. But coding agents took my front end work to an entirely different level. Agentic-Nets OS needed a visual net editor. Drag and drop places and transitions. Connect them with arcs. Inspect tokens in real time. Edit inscriptions with syntax highlighting via Monaco editor. Manage sessions and workspaces. The kind of sophisticated, interactive UI that normally demands weeks of focused front-end work per feature. With coding agents, I could describe a component in the morning and have it working by lunch. Refactor after testing, improved version by afternoon. 37 Angular components, each generated through precise specifications and iterative refinement. The drag-and-drop editor, the token flow visualization, the session management panel, all built at a speed and polish that would have been impossible working alone. The AI was remarkably good at Angular patterns. Data tables, forms, navigation, settings pages came out clean and consistent. Where it needed human guidance was the novel interaction design, how the net should zoom and pan, how tokens should animate, what the element explorer should look like. I made those decisions. The AI implemented them. And the results were better than anything I'd built before. The nets that prove it works. Let me tell you about specific systems running on Agentic-Nets OS. Not hypothetical. Running systems with real metrics. The Bootstrap agent. Every workspace needs initial tokens. Previously, a shell script made 9 fragile API calls. I replaced it with a single agent transition that reads a JSON definition and self-populates the workspace. 9 tokens created, 11 iterations, 6 minutes and 48 seconds, 0 failures. And while the Bootstrap agent was still creating tokens, the net's verification transitions had already started firing. The net didn't wait. It began working the moment the first token appeared. Concurrent execution, emerging naturally from the Petri net semantics. The self-improving log analyzer. 19 places, 12 transitions, 6 functional zones. It ingests system logs, identifies error patterns, investigates root causes, and learns from each investigation. When it encounters a pattern for the first time, the agent transition fires, reasoning through the error chain across services. That analysis includes a reusable signature that crystallizes into a deterministic matching rule. Next time the same pattern appears, a past transition matches it instantly. 0 LLM cost. The same error that took 47 iterations on day 1 required 0 on day 4. 500 times cheaper. Not because the model got smarter, because the net learned. The 25 cycles net. A closed feedback loop that reads its own execution logs, proposes code fixes via Claude CLI, applies them, rebuilds services, and feeds a new task back to the beginning. 25 complete cycles. 6 hours. 0 human intervention. After cycle 1, 1 context token. After cycle 15, 15 tokens, and the agent avoids mistake from cycle 3 without being told. The cost curve bends downward because context accumulates. Each cycle's report becomes documentation for the next. The reflexive brain. 15 places, 18 transitions, 42 arcs. A 5-step reflexive loop. Ask questions about its own code base, generate answers, identify gaps, investigate, synthesize. After 3 cycles, 31 knowledge tokens, 12 architecture insights. Knowledge accumulates in a context place with non-consuming reads. The answers don't get smarter. The context gets richer. The full stack. 10 services. The node for event sourcing. The master for orchestration and AI. The GUI for visual editing. The gateway for OAuth 2. The executor for distributed commands. The vault for secrets. The CLI supporting 5 LLM providers. The Telegram chatbot. The blob store. The monitoring stack. Every transition emits metrics. Every token movement is traceable. Complete observability. A Jenkins pipeline deploys autonomously to staging. 42 blog posts at alexcjsaylor.com documenting the journey. Business source license converting to Apache in 2030. What works and what doesn't? What works brilliantly? Speed of experimentation. 3 persistence models tried and discarded in a week. Spectus system generation. 42 endpoints from 1 OpenAPI doc. Consistency. The 100th boilerplate function as clean as the first. Multi-model review. Different models catch different blind spots. What doesn't work? Security. AI catches known patterns but can't think adversarially. Assumption challenging. Nobody pushes back on design decisions. Context loss. Every session starts fresh. No ambient shared understanding. The model teaching problem. Petri nets have limited training data, so every session requires partial reteaching. Emotional isolation. Solo victories with no team to share them. Documentation of intent. AI generates API docs beautifully, but can't explain why the system is designed this way. What comes next? Pattern crystallization. When you collaborate with an AI agent, workflows start creative, reasoning, experimenting, correcting. Over time, the same sequences repeat. At some point, a workflow becomes procedural. That's when a pattern crystallizes into a net. Two execution strategies emerge. Engine executed. The Petri net engine runs deterministic steps, calling AI only where needed. Lower cost, auditable. Agent executed. A global AI orchestrates the entire net as a structured plan. More flexible, higher cost. The deterministic first principle drives the economics. Every workflow starts with AI executing everything. As patterns stabilize, transitions crystallize from agent to map, from LLM to pass. The cost curve bends downward, the opposite of most AI deployments. The package registry already exists. Publish a net. Search for patterns. Install pre-built workflows. Share solutions across organizations, like NPM, but for governed agentic workflows. And the reflexive capability points towards something I hadn't imagined when I started. Nets that monitor their own performance, identify degradation, propose optimizations, test them in dry run mode, and deploy under human approval. Self-improving systems governed by the same Petri net formalism that makes them auditable and safe. This story is not about replacing teams. It's about what becomes possible when deep architectural knowledge meets AI implementation speed. The Petri net idea waited 20 years because the gap was too large for one person. Coding agents closed that gap. Tireless implementers translating architectural vision into working code at a speed that made the whole project feasible. Every turnaround, every moment I changed direction, refactored, tried an alternative, was made possible by that speed. With coding agents, the cost of improvement drops to nearly zero. And when improvement is cheap, you improve constantly. The architecture gets cleaner. The system gets more coherent. That is the real power. You can build what you actually envision, instead of the compromised version that fits within traditional constraints. Agentic-Nets OS is the system I envisioned in that lecture hall 20 years ago, more sophisticated than I could have imagined then, built with tools that didn't exist until last year. The idea doesn't have to wait anymore.